Okay, it didn't say 3, 2, 1, but it went beep, beep, beep. So, anyone want to try and feel confident enough to share what they put that they think you might get full marks to? Go
on. This ionisation is done when electrons of high kinetic energy are fired at the sun using the electron gun.
Yep. I'm trying to remember without looking what the answers were. Can you see how sometimes I write my things in a slightly strange way? Because I'm doing bullet points without the bullet points. So I've got high-speed electrons from an electron gun are fired at the sample and knock out one electron. So there's only one other thing that I think she might have needed to get the mark. What do you end up with at the end of that? You end up with
iron and then 2 electrons.
Yeah, what kind of iron?
Like +1.
A +1, yeah? So boron, 1 plus iron. Yeah? I would maybe include a little equation to tell me what the thing is. I'm reading it just to see, did they ask me about a specific thing that they put in? No. So I can use X. So I've got X gas plus an electron. So X plus gas plus 2 plus 2 electrons. You don't have to use a different line each time you want to make a point. For me, it helps me to count how many points I think I've made. But if anyone didn't like bullet points, then I'm not upsetting them. Personally, I like bullet points, so I just put them in. Yeah?
Do you ever need to include the bit about dissolving it in a...
If you did that beforehand, in this it just didn't get a mark. But I might include it just to be on the safe side. I heard a few of you saying that. I'll show you what was actually on the mark scheme, although it'll probably show you the one after it as well, so I might do it quite quickly. So you can see, not being fast enough so you can see the next one. Oh, I'm trying to make it so big that you can actually see me move it. But I think I've backfired by going too much. So high energy electrons, just to hope you're going the wrong way now. This is going really badly. How can I get it to actually do what I want? I can only get it to go one direction. Oh, there we go. There we go. I'm going to see if I can sneak it up. Now, this was made before there'd ever been an exam on this, which is why it says example answers, because they weren't exam questions. They were just questions they came up with right at the beginning. We've got high energy electrons from an electron gun, fired at the sample, knock off one electron. It doesn't actually have to form 1+ ions, but I think it's useful to include that. But that's what they have. Okay? Is everybody okay with that? We'll look at number 2 at the same time, since I pretty much showed it to you anyway. So number 2 is the one that's not got as many examples of exam questions, but you can see here they did include a volatile solvent, so it's weird that they didn't in the other one. So you might as well include it in both, just to be on the safe side. So sample dissolved in a volatile solvent, injected through a fine hypodermic needle to give a fine mist or an aerosol. The tip of the needle has a high voltage, and it gains a proton as it leaves the needle. And I think this came up either last year or the year before, and people did find this one harder. So I would certainly, that's not going to work, I would certainly recommend having some kind of flashcard to help you to remember that one, because it is just really a memorising to get those actual specific key points in. So I'll pause this recording. Okay. I've just put up the answers to the next few. What's important with the equations is that Yidi mentioned that calcium would usually form a 2+ ion, and she's right. If I was writing an equation to help me to find the formula of calcium, if I was trying to think what's the formula of calcium carbonate, what's the formula of calcium chloride, it's really important I remember that it's normally going to form 2+. But in the mass spectrometer, we make all of the samples 1+ ions, even if that's not the type of ion that they would normally form. And we have to remember the state symbols here. We start with the sample as a gas, and we end up with the gaseous positive ions. Okay? If we take a molecule, we end up with the whole molecule with a positive charge. So we haven't changed any of the atoms in this at all. This here, this is called the molecular ion. And a molecular ion is the whole molecule with 1 electron knocked out. Okay? But it still has exactly the same mass as the whole molecule, apart from that negligible mass of the electron that's been knocked out. Yeah. So you're allowed to do it that way as well. Yeah, I could have written Ca gas plus an electron goes to Ca plus gas plus 2 electrons. That would also be right. Okay.
So it's just added.
Yeah, in this one, they've cancelled that electron out. Yeah, but it's okay in this particular example not to cancel them out. Both of them are correct, either with 1 here and 2 there, or with it cancelled out on the left side. It wouldn't matter. Yeah, so that would be the same for this one as well. I could have put plus an electron and put 2 there, okay? That would have been correct as well. And then when we do electrospray, in electrospray, we add a proton, so it's different this time. The sample is usually gaseous, but you can see they didn't put the state symbols here, so I don't think they're as essential here as they are here. But here, we do have to group all the H's together. And that, when I did this question, I think I didn't do that. It didn't occur to me that I might have to do that. Obviously, if it didn't have any H's in the beginning, then you could just add the H at the end. But most of the time, we're dealing with organic compounds here, and so they usually have carbons and hydrogen. And then did this question ask you how they get accelerated? Yeah, so they get accelerated as they're attracted to the negative plate, or you could say electric field. What was that?
Why do they use it?
Oh, is that what it says? Why do they use it? It's a pretty rubbish question. But yeah, obviously it's crap. Isn't that one worth 2 marks? Yeah, I don't understand why that one's worth 2 marks. I think they made a mistake because there isn't really big things you can say there, is there? Has anybody got any questions about those ones? Anything anyone's not sure about? Remember, even if it seems a little bit stupid, don't be afraid to ask. So every time I talk, I'll restart the video. So I'm going to pause it again, but we'll have all of these things on the little video. I've not paused it yet. Is that paused? There we go. Okay, so for the next ones then, if I can get it to scroll. Oh no, I don't know what I've done now. That's my fault. Let me go back. If I did. So we were roughly here. Okay, so when the particles, the ions are accelerated, what's important is that they all end up with the same kinetic energy. Remember, because then we've got kinetic energy equals half mv squared, and that means that the lighter ions will have to be travelling faster in order to get the same KE as the heavier ions that have to be travelling slower. So the time of flight depends on the mass of the ions, with lighter particles travelling faster. or you could say with heavier particles travelling more slowly. I now can't see the question at the same time, so I'm just going to have a look back at what 3.2 even said. So 3.2 said which of these ions will reach the detector first. So lighter ions will always move faster and so will be detected first. So the only difference between these two ions is their mass, and the 79 is the lighter one, so it would reach the detector first. Same thing here. The only thing that's different between these two is the mass. This has got a heavier isotope, this has got a lighter isotope. So this one's going to reach the detector first because it's the lighter of the two ions. Okay? So you just have to identify the lighter ion and then say because it's lighter. Does everyone understand that one? And again, I can't see that what 4.1 actually says. Here we go. What isotopes are present in this element? Hopefully you can see that it's gallium. And so we've got gallium 69 and gallium 71, which is why we've got these answers down here. Is everybody okay with those ones so far? Yeah? Anybody got any questions about any of the ones that we've been looked at so far? All right, I'll pause this again and we'll go through some more in a bit. I know some of you have got further than others. More. There we go, it's recording again. So the next one was working out the relative atomic mass. And actually, compared to some of the other ones we've done, hopefully you found that one relatively easy. It should be 69.8. Yeah, to 1 decimal place. I'm going to go back to here. I know some of you, is everybody okay with that one? But this one, people usually find a bit harder. So I wanted to spend a little bit more time explaining this one. So in this one, we have got an element, but it's not atoms of an element. They've given me the formula. This is molecules of an element. And so when we've got more than one atom joined together, we do end up with a more complicated spectrum. Chlorine's got 2 common isotopes, 35 and 37. And so what I can do is have these joined together in different combinations. So I can have 35Cl joined to 35Cl to make a molecule of chlorine. And that one would have a mixture of 70. Does that make sense? And so that's what I can see here. Yeah? Does that make sense or not? Yeah? So what I have to write here, and be really careful here, because some of you might have got this wrong. So that's my molecule that's got a mass of 70, but read the question. It says, identify the ion responsible for the peak. So if I write that, I actually don't get a mark, because I haven't identified an ion, I've identified a molecule. And the molecule wouldn't have actually been detected at all. It wouldn't have made it through the mass spectrum to the detector because it wouldn't have been accelerated and it wouldn't have been detected. So I do then have to put that plus next to it. Okay? Because whilst that was my original molecule, the ion that was responsible for the peak has to have that 1 plus charge. Does that bit make sense? So I can also have a 35Cl joined to a 37Cl like that. There's my covalent bond joining them together. And that will have a mass of 72, because 35 plus 37 is 72, which is going to be my mixture of that one. This one's not so nice to write. I have to write 35Cl, 37Cl. And again, I have to put my plus because I had to identify the ion that was responsible for giving me that peak.
So you don't need to do classes separately, let you join.
Yeah, these are 2 atoms joined together. So if I had like I know this isn't covalent, but when I have NaCl, what I've done is I've knocked one electron out of the whole thing. And that whole thing has a plus. If you wanted to, you could do it like that. It doesn't have two pluses. I've knocked one electron out over the whole thing. Okay? And so this one is the final combination that I could have, which is 2 lots of 37. 37 Cl2, and again, it has a plus. Is everybody okay with that? In the past, I had set this as a homework, and very rarely did anyone manage to get the marks for this part. A lot of people did come up with the formulae, but it's often this plus charge that catches people out. So make sure that you always read the question, because there's another part that you'll see in a few lessons' time where it always says identify the ion, give the formula of the ion, and people don't put an ion, they don't put a charge on it. If you've not got an ion when it asks for an ion, you're not going to get the mark. Yeah, even if you had to think quite hard about the formula of the thing you wrote, if you forget the plus, you lose the mark. You've only got one. Okay? I'll pause it again because I'm not sure how many of you would have got past here, because I know some of you would have done, but some of you might have been finding that one a bit hard. So we'll pause again. These last ones then. Okay, don't worry if you hadn't quite finished them. We'll have a look. So in this one, what's important when you're looking at the mass spectrum of a molecule, a hydrocarbon is telling you it's a compound. It's got hydrogen and carbon in it. And so this is a molecule. And so that means that it can fragment. We shouldn't have to worry too much about these fragments, but it is possible for it to fragment. Yeah? When we look at the mass spec of a molecule, we focus on the very far right, the highest numerical MZ values. And hopefully you can see that this is very small and has a mass of 1 unit higher than the one previous to it. And so this is our molecular ion peak. And so this will tell us the MISTR, which is 56. Is that okay? And all those other things down here, these are actually caused by fragments. Annoyingly, that is, I think, the only time you would ever have to write fragments. You can see due to fragmentation. You should never really have to worry about fragments, but I think it can be useful to be aware of why those peaks are there. And then we've got why is there a peak with a higher MZ ratio? So they're asking, why can we see this little peak here? And that one is there because some molecules contain these heavy isotopes of hydrogen or carbon. Okay? And then for number 7 is one that the first time I did these questions, I got it wrong. I like to confess my mistakes. The more I confess them, the less likely I am to make them again as well. So don't be embarrassed about your mistakes. Say them out loud, circle them, highlight them, admit to them, and then you won't make them again, hopefully. So when I looked at this, I instantly just went for this one. But what we have to remember is that in electrospray ionisation, we add H+, therefore we add +1 to the mass. And so what I have to do is 485.1 minus 1, And you'll be amazed how many people can then get that maths wrong. Yeah? I would recommend using a calculator to do the most basic maths, because in an exam, you can get a whole load of very weird answers here, including most common 485.0. People take away 0.1 instead of taking away 1. Yeah? So it should be 484.1. That should be the answer. But I'm sure you can see how in an exam, it seems stupid that you could get a -1 sum incorrect. But I have seen it happen many times. Okay? And this one, again, here, this is caused by 13C or 2H.
I think it is.
Is everybody okay with that? You should see, I've managed to write exam papers where the questions have gone 1, 2, 3, 7, 8, 9, 10, that kind of thing. And I've like proofread it 20 times and missed the fact that I completely can't count. I've got ways of checking now that help me, but still can't be trusted to count to 10. Okay? So this one was just a rearranging thing, and the steps are there. And it's basically that's what we had to do last time, almost. This bit here is you have to do, I think you guys call it kiss and flip. I don't understand how you're supposed to explain that. I've asked mathematicians how to explain kiss and flip, and they just say it's just kiss and flip. So apparently you guys are okay with that. I was hoping for a more sort of robust sounding explanation, but I haven't managed to come up with one. Apparently you guys will be okay with that. And there you can see the final answer as well, which I'll just leave up for a minute.
I don't understand
Which one?
6.2. Just the wire. Oh no, wait, why it has been arranged. Wait,
Let's go back after you can see the graph. So this is our molecular line, yeah, the mathematics. So finding why is there something that's higher enough to this? This tiny temperature is not high enough to this. That's caused by the presence of heavy hydrogen, 2H, or heavy carbon, 13C. No, because that would give it a 2 mass unit higher, and the likelihood of having 2 heavy isolates in one molecule and being sufficient to be detected is very small.
yeah, and the graph is like
So this is the whole thing. Yeah, this is the most abundant. That tells you this is the one we've got most of, so it isn't the MR. The MR is always the one with the highest interaction number. Okay. So what I want us to do now is to carry on with the notes, which means looking at something a little bit different. That's the end of the maths spec part, and hopefully this would have helped to answer some of the little questions you might have had without even knowing you had them. Yeah, and then we're going to move on. What's up?
It's like 6.3.
Let's look. This one.
Yeah.
So you know how there's only one little peak? Have a look at the little graph. So can you see that is our mixture? This is it. And it's saying why is there another one? Why is there something the higher end there down here? The only peak you've got is a higher end. And that teeny one is caused by the presence of either that heavy isotope or that heavy isotope.
Why was that?
There are enough. So those isotopes are rare, but not so rare that they won't be in a sample in a million. And so you get they're rare enough that you wouldn't get both of them in one molecule, or if you did, it would be so unusual that it just wouldn't even show in the graph. But you tend to get these tiny little peaks because there's enough molecules that have one of those in them that we get a little tiny peak. Yeah? Okay. Anybody got any other questions about this before we move on? Okay. So let me just get rid of this bit then, and we'll go back to the class notes, and that means we are now here. Yeah? Okay. So if you can stop talking now, guys, make sure you've got your notes because we're going to carry on with those. Okay? What we're going to be doing in the next few lessons is looking at atomic structure a little bit more and trying to work out how electrons are arranged in atoms and the evidence that we have for how electrons are arranged in atoms. So you might remember, if you watched the springboard videos, that electrons aren't arranged in quite the way that we learned at GCSE. If you didn't watch the springboard videos, don't worry, it doesn't matter. As far as you're probably concerned, electrons are arranged kind of like that, yeah? Where we've got the first shell can hold 2 electrons, then 8 in the second shell, 8 in the third shell, and we only ever had to worry about there being 2 in the fourth shell because you only have to draw up to calcium. Yeah? What we're going to look at is, how do they know that? Where did they get these ideas from? Can they look at them? Not really. They're really small. So how are they going to get evidence to help us appreciate how many electrons are in each shell? And we're going to do that by looking at a concept called ionisation energy. So you need to learn the definition of first ionisation energy. This is definitely a flashcard kind of statement. It has to be memorised. So first ionisation energy is the energy required to remove 1 electron from each atom in 1 mole of, and this part's important, gaseous atoms. So we have to start with atoms as a gas. So even if our substance is something like carbon or sodium, which would usually be a solid, we want to be measuring just the amount of energy needed to take an electron out. And if we start with them as a solid, then we might be using up some of that energy to break metallic bonds or to break covalent bonds within the structure. So what we do is we turn them all into gases first, so that then we're comparing like with like. We're now only looking at the amount of energy that's required to remove an electron. So it's required to remove 1 electron from each atom in 1 mole of gaseous atoms to produce 1 mole of 1 plus gaseous ions. And it does not matter if the atom doesn't normally form 1 plus ions. So we can still do this for chlorine, for oxygen, for aluminium, for things that might form other charged ions as their preference. Like, not that they prefer anything because they're just atoms, but even if that isn't the ion we would usually associate with that element. So we start with our element and we turn it into gaseous 1 plus ions and an electron. This is actually the same as the ionisation equation in the mass spec, if we cancel the electrons out. But what's important here is that we'd always be starting with 1 mole of these in order to make this fit the definition. And so, second ionisation energy is when I take the product of the first ionisation energy and then take another electron away. So this time it's the energy required to remove 1 electron from each ion in 1 mole of gaseous ions with a 1 plus charge to produce 1 mole of gaseous ions with a 2 plus charge. So for second ionisation energy, we always start with a 1 plus, and we turn it into a 2 plus. So second ionisation, I'm looking at making a 2 plus as my product. Doesn't mean I'm starting with a 2 plus. I want my 2 plus to be my product. And I'm only removing 1 electron because I started with a plus already. So I don't have 2 electrons here. My overall charge on the left-hand side of my reactants is 1 plus. My overall charge on the right-hand side of my product is also 1 plus. My charges should balance always on both sides of the equation. Okay. So have a go and see if you can write them. First, ionisation energy of sodium, and the second ionisation energy of sodium. Okay to me. Where does it go? Where does the iron go as well? Where does any of it go? Doesn't matter. In theory, it would be attracted back to it again. So you'd have to manage to get thoroughly part of
We
it.
just got rid of the electrons through the second ionisation.
Yeah. But we're not. This is a standalone equation for second ionisation. So we're not necessarily saying that we did that one and then we took it and we did the next one. We have to be getting rid of these electrons somehow.
But you would have to have the first one in order to have it.
Yeah, you'd have had to have the first one.
So you just ignore the electron.
Yeah. Yeah, you're looking at it as a standalone process. We're not looking at it as an overview process.
Do they do this more than twice?
Yeah, you could do this 3 times, 4 times, but it's going to take more energy to do it the more times.
Yeah.
Because we'll have the balance between protons and electrons is going to get smaller. There'll be more protons attracting fewer electrons, so they'll be able to attract those more strongly than they could before. They're not going to have to share that attraction out as much as they have before. So with this one, you should have had sodium gas goes to sodium plus gas plus an electron, whereas here sodium plus gas goes to sodium 2 plus gas plus an electron. Okay? And really don't worry if you're writing ions that you think, but it would never do that. It's going to do it here because I'm going to make it do it. That doesn't mean it's going to be easy. Sometimes it's going to be really hard to make some of these ions. But what we're looking at, what we're interested in is how much energy it takes to do that. Because when things form ions, we're going to have, usually they just won't lose an electron just like that. Even with sodium, it had that electron was attracted to the nucleus. It was part of that atom. So it's going to take energy to pull it away from the attraction to the nucleus, even with something that likes to form a 1 plus ion. But then later on, we hope that that ion would form an attraction with another ion, and then it gets that energy back again from that attraction to something else. So usually, bonding is some kind of payoff between how much energy it's going to take to form something in the first place with how much energy I'm going to get back when it does it later on. I'm not usually going to get this ion because actually the amount of energy it takes to form, I'm never going to get back. But I can still do it if I want to. It just means that this wouldn't happen naturally. Naturally, it wouldn't form a 2 plus ion because it would take so much energy for me to pull that electron away that I wouldn't be able to get it back in a reaction. So it just wouldn't be energetically favourable. It wouldn't make sense in energetic terms for it to do that. just like, you have to think of these things as like transactions. I might go and pay £1 million for a really nice big house because the house would be worth it. I wouldn't go and pay £1 million for a shed because it wouldn't be worth it. What I get back at the end has to somehow be worth the money that I put in. I'm going to take a lot of energy to do this. If I can get enough back afterwards, it's worth it. Here I'm not going to most of the time. But we're going to have to look at ionisation energies over the next few lessons, and we're going to look at what's going to affect how big they are, and then we're going to start looking at some of their numbers. So if I want to take an electron away from an atom, there's a number of factors that are going to affect how much energy it takes for me to pull it away. So if I hate not being able to touch anything, because usually I would just come and steal all your stuff. And I can't because I'm not allowed to touch it. So I would have stolen Anisha's pen. And how hard it is for me to do that depends on how much she likes the pen, really, doesn't it? Some of the pens you might be like, no, I take it. I don't like it much anyway. She might not be attracted to some of her pens very much. Not that I'm saying she really likes pens, how are we going a bit far? But others of her pens, she might be like, whoa, I got that for Christmas from my best friend. I love that thing, get off. So it would take a lot more energy for me to pull it away. So we have to think, what's going to affect how much energy it takes for me to pull an electron away from an atom? And there are 3 things that are going to affect it. The first one is the attraction of the nucleus. If the nucleus has got more protons, it's going to be hard to pull an electron away. Does that make sense? Yeah? So, the more protons in the nucleus, or we can say the greater the nuclear charge, the more energy. I can always write as much as I like in these boxes and you can't. The more energy it takes to remove our Is everybody okay with that idea? The positive protons in the nucleus are attracting the negative electrons in the shells. If I've got more positive protons in the nucleus, then they're going to attract those electrons more strongly, and it will be harder to take them away. But that's not the only factor that affects it. So the next is how far away the electrons are. So if we take a little tiny atom like helium, in its nucleus, and it's got 2 little electrons in the nucleus. It hasn't got that much positive charge, but these electrons are super duper close. They can get really close to that positive charge, so they can kind of really experience it. If I've got a much bigger atom, it might have more protons in the nucleus, but my outermost electron, the one I would take away first, can you see, is actually quite far away. And the further away it is, the less it's going to be able to feel that attraction from the nucleus. So the further the outer electron is from
Yeah, but that's the same as
So the more protons in the nucleus, the more strongly the electrons are attracted to the protons, the harder it will be to remove them. But also, if they're close to the nucleus, they're going to be more strongly attracted. But if they're further from the nucleus, they're going to be less strongly attracted. A kind of useful analogy can be to think about being at a concert. If you're in the front row of the concert, you're very attracted to the band. You're not going to go for a wee, even if you're really desperate. Not that you're going to be able to go to a concert anyway, but you're not going to move from that spot. You're very attracted. You can see everything. It's great. You're right at the back of the concert with 75 rows of people in front of you, if you're lucky. You kind of need a wee. You just go anyway. Because you couldn't see anyway. You could only see people's heads. You weren't really very attracted to the people on the stage. Yeah? Right. You can ignore the concert analogy.
Well, just with that, does that say it is attracted to it in the left?
That's an and.
Oh, sorry.
I don't worry. So sometimes my hands are beautiful and obviously an and sound, and sometimes they're a small scribble that could quite frankly be one of about 75 different characters. So don't worry about that. Just check.
It is very
That one, good. This one.
good. The handwriting.
It's like, yeah. That was where whiteboards were always. These are pretty good, but my old whiteboard writing was beautiful. People would take photographs. Okay. And then the last thing, that didn't really work. Oh, I didn't want it to do that. I wanted it to do that. Because I've moved it to the other side. Good job that didn't do anything. So the last thing that could affect it is this thing called shielding, which again the concert analogy is quite good for. So if you're in a small venue and you're far away and there's not very many people at the concert, you can still see. But if you were at a packed venue with loads of people in the way, then you wouldn't be able to see. You could be the same distance. I could be sat there, could be my stage here. Here's me, looking happy. Yeah. But then there's loads of people. I can't see, and so as I always need to loo, I just go to the loo. Yeah, and then I think might as well get home. But here's me, and here's the stage. This isn't a very good band, so not very many people came. I'm still the same distance away, 3 meters ish. I have no idea, that's not very far. But anyway, 3 meters here. But here I'm sad, and I leave. Go to the loo, go home, get a taxi, the bus, it's a bit tight. And then in this one now I can still see, so I stay. Yeah? So it's not just about distance, it's also about how many things are in the way. So we've got how attractive the thing was over here in the first place. There are some bands that I'd be really keen to stay for and some I wouldn't. How far away I am from them and how much stuff there is in the way. Yeah? So shielding of the attraction to the nucleus means how many electron shells there are in the way. So the greater the distance, the more the shielding always anyway. So these two things come together. Yeah? But by shielding, we mean if that's my nucleus here, then here I'd have 1, 2 shells in the way that stop my electron from being able to feel that positive charge. And so we say that these inner shells of electrons are shielding the outer electrons. They're kind of blocking the view, blocking it from feeling that positive attraction. So the greater the number of inner electron shells, the more the outer electrons are shielded from, I can't spell shielded, I'll just confess to this now, are shielded from positive nucleus the less attractive they are to it. It's very embarrassing, my IE issue, because Mrs. Nareed is called Sheila. I can't spell her name. Every time I have to write it at least twice. Usually I have to write the two possible ones, then look at them for a little while, then try and work out which one was really right. And I've worked with her for a long time now. Fortunately, my email does know how to spell her name, and it kind of auto fills. But if I was writing her birthday card or something like that, fortunately, I don't know that many Sheilas, so it's not that common a problem for me. None of you have IE combos in your names, do you? I can do that one.
Imagine ROSEI.
I have heard the letters, but not
together, yeah.
You got the song.
I'm okay, I can spell your name down. I just can't do it. So every single time I see words like shield, I get them wrong every single time. And I know that I'm talking except after 16. But with Sheila, Sheila is like Esau. Yeah? So Sheila does it backwards, and that means the word shield is now impossible.
She just decided that she
See? Not right. Right. So how am I supposed to spell the word shield when it's actually like that? They all just look horrible to me now, and I just can't deal with it. So I'm just going to say I can't spell it. You have to learn to accept
You could
that.
just call her that.
She did like
Happy birthday. You have
Would you do it with an E or with an I?
She's really good. She's
I think she prefers to be called Sheila. So guys, back off my inability to spell back onto chemistry. So when we're looking at trying to compare these numbers, we haven't looked at any numbers yet. But if we were trying to compare them, if they're different, we need to think, well, why might they be different? Which one would I expect to be bigger? Which one would I expect to be smaller? And think about these factors and which ones might be causing those differences. So let's see. Okay. So what I can do with an atom, if I had a lot of energy and a very special machine, is I could take each electron away one by one. That's what this thing means by 6 separate. So it means that I've started off with my sodium gas, and then I've taken an electron away, and I've made sodium plus gas. Then I've taken another electron away, and I've made sodium 2 plus gas. Then I've taken another electron away, etc. But I'm doing this one by one by one. So this would be my first ionisation energy, my second ionisation energy, my third ionisation energy, etc. Yeah? And so this is showing my first ionisation energy here. Yeah? So it takes quite a lot of energy to remove the first electron. You can see it's a log scale, which means that we're going up by a factor of 10 every single time. So it's quite a big amount of energy that we're looking at. So if we look at what we know our structure of sodium to be, sodium's got 11 protons, and it's got 2 electrons in the first shell, and then it's got 8 electrons in the second shell, like that, and then it's got 1 electron in the last shell, like that. Yeah? So for that first ionisation energy, when we do these ionisation energies, we always take away that electron first, and then we work our way in. So I'm taking that one away here. Yeah? Once I've taken that one away, I'm going to end up with this. And then I'm going to take the next electron away. So can you see, I'm now going to take one of these away. I could have picked any of them in that shell. But can you see I've now got this jump where it's suddenly taken quite a bit more energy than it did before. And so this was a piece of evidence. Can you see we've got this big jump, but now can you see it's quite gradual? But what we've got is we've taken away the first electron, but then the second, third, fourth, fifth, sixth, seventh, eighth, and ninth have been a little bit easier to remove, but not with a big jump. I mean, a little bit harder to remove, but not with a big jump. They've got this nice gradual pattern, and that this would be the second, third, fourth, fifth, sixth, seventh, eighth, and ninth. Yeah? But once I've removed the ninth electron, you see I'm then going to have to move in a shell. And that corresponds with another jump. Yeah? Now I've got to a shell that's closer to the nucleus and less shielded by inner electron shells. And so it's suddenly quite a bit harder for me to take my electron away. And now I can remove number 10, which is here, and number 11, which is here. Once I've got this, now I've got no more left. Yeah? All gone. It's just a fact. I can't take any more electrons away, they're all gone. Yeah? So, scientists were able though to look at a graph like this and think, obviously now we know that that's the arrangement of electrons in a sodium atom. But this would have been a piece of evidence that they could use to suggest that they were arranged in these shells, with 2 electrons in the shell closest to the nucleus, with 8 electrons in the second shell, and then here this only had 1 electron in the shell that was furthest from the nucleus. What people can find a little bit hard when they have to look at these graphs is that we're getting closer to the nucleus this way. Yeah, so this was my furthest away from the nucleus, my outer electron. And then when we draw a picture of an atom, we always start in the middle, don't we? And work our way out. But this way, they're working their way in. So you're kind of drawing the atom in reverse to what we're used to. And so sometimes people can find that a little bit confusing when they're trying to work it out. But can you see that does provide some evidence about how the electrons are arranged? In order to explain these jumps, they proposed that they were in these shells, these areas of space that had a slightly different attraction to the nucleus. Okay, so why are there big jumps after removing the first and the ninth electrons? Why were there the bigger bits? Why were there?
Because they were changing shells.
Yeah. Because the electron removed was in a shell that was closer to the nucleus and less shielded by inner electron shells, and therefore more attracted to the nucleus. So this one is explaining why we've got the jump here and the jump here. Yeah? There's kind of blips in the pattern. So now it's asking, why is there a general increase? So if I just look at the whole graph, can you see it's generally going up the whole way? We have got two blips where the increase is more than we were expecting, but on the whole, it's going up all the time. So why is it just going to go up between here and here, for example? Why is it going to go up between 3 and 4, or between 4 and 5, or between 5 and 6? Why is it going to be harder to do Na 2 plus to Na 3 plus an electron? Why is it going to be harder to do this one, where everything's gassed up on top to write the gases? You answered the last one, yeah.
Is there a few electrons to be attracted to the nucleus and but
Yeah.
they're attracted
So, as electrons are removed, there are fewer electrons attracted to the nucleus. It is harder to remove electron from positive ion. There's greater attraction between the nucleus and the remaining electrons. And so there's the little picture that I drew before. It's just really hard for me to get everything in the right page. You can often see more than I can. But before we knew what we already know about the structure, this helped to provide evidence that this was the structure. This helped to conclude that perhaps there are these different energy levels because we're getting these groupings as we go. And that perhaps each energy level could hold a certain number of electrons because we have 8 here and 2 here. And that for sodium, the electron configuration is 2, 8, 1, or that's the picture that goes with the or. It's just perhaps not particularly obvious. Yeah?
I didn't really understand how the answer explains the question.
So for this one or this one?
The second.
So in this one, what it's trying to say is like, as I go on the bit that just looks like that, yeah? Here I'm in the same shell. Yeah, so if I was trying to take away this electron and then this electron, they're the same distance roughly from the nucleus, and they've got the same amount of shielding. So why is it harder for me to take this one away from this one?
Because there are fewer.
Because there are fewer. Because now this nucleus that has 11 protons in it is only attracting the remaining electrons. And actually that does make it slightly smaller. Each time we take one away, because it's able to attract the remaining ones that little bit more, they actually do get smaller.
So what's it mean by in successive ionization?
So that the successive thing means as I go from one to the next,
Okay.
yeah? So as I go from 11 to 10 to 9 to 8.
So increasing trend means like getting harder to.
So yeah, why is it taking more energy as I take each extra electron away as I go from 11 to 10 to 9? Okay? We're going to stop there. Your homework is on Google Classroom. It's always going to be set on Monday and due on Monday. But like I said, it isn't printed out. But don't feel you have to write on a screen. You can just write answers on a piece of paper. If you can print them out, that's fine. But if you can't, just write them on a piece of paper. Then please scan and submit. There were a few people that didn't submit. The one from 2 weeks ago. I would have sent you an email if you hadn't submitted it. If you haven't got an email from me, don't worry, it means you submitted it. I can't take in the paper. So can you can you scan it to PDF and submit it there? You don't have to do it this second if you've not got time. If you have, that's fine. But I'll give you a little bit of slack. Unfortunately, on Google Classroom, it shows us late if you miss the date and time that I originally set. So, but I would make a sort of mental note. In my comment, I would write it was late to remind me it was really late, as if not isn't an hour, because it will show whether you're an hour or 5 days. It shows the same on Google Classroom, and one of those to me is irrelevant. Now, but 5 days, nothing more. But you clearly got it in front of me.